So what we're going to be doing here is looking at using Mathematica to predict the Supreme Court. And I've gotten down to here in the code in which I'm going to create this data set for the first time. And so what having it as a data set does is it enables you to access elements of this data set in a way that's more similar to that which is available in our data frame. It's a little more friendly. And we'll see examples of that below where I'm going to use queries on the data set. And in fact, there are lots of things that one can do once it's in a data set. The other thing I'm going to do is to get something out of a data set, what you need to do is to, if you have an association, let's take the first row of this data set here. And you can see it's a description of this case. It doesn't have everything. I see those little dots, 37. That means there's more stuff. But the way you undata set it is you wrap a normal around it, and now it just looks like an association. And if I wrap normal around it again, it will then just look like a good old-fashioned Mathematica list of rules. So there are ways of getting things in and out of data sets, and the key command you need is normal. So what I want to do in order to get our data into a form that Classify likes, which is what I'm going to be using down the road, what I'm going to do is I'm going to take normal of the data set, and then as I've done before, I'm going to take for each row, I'm going to take most of the row and the last element of the row. So that, and that's going to create it's going to put the data in the right kind of form. So let's see if we can see that for a moment. Let's see if we can. If I say machine learn form of DS, what it's going to produce is, take a moment. All right, it's going to produce a list of associations. And you can see that it's saying, okay, the law type in this case is 6, and the majority opinion writer was justice number 78, and the spinning beach ball has me worried. There we go. And was it a split vote that has a 1, etc. So all I'm trying to do is to get this code in a form that Classify can use. Finally, there are some nominal variables that we're going to be looking at. And so I'm just going to make a list of what are the nominal variables here. All of these are nominal. One of the things I'm going to do later on is what I had you predict was whether the justice's decision would be liberal, according to the Washington University of St. Louis, or conservative. And it occurred to me at some point that perhaps one of the reasons that what we're going to see is that these predictors don't work real well is that that's a subjective thing. It's a little bit arbitrary. And so maybe what we should be predicting is instead whether the case was affirmed or reversed or the actual disposition, which is somewhat easier to figure out. And so one of the things we'll look at is whether that improves matters, and I think what we're going to find is that notwithstanding my brilliant insight, it doesn't really improve very much. All right, and so then the other thing I want is just a list of independent features, the things that we're going to put into our formula. We're going to know the petitioner, the respondent, the lower court disposition, the lower court disposition direction, the issue area, and the law type. So we'll just create those things. All right. So let's start creating some data sets. And the data sets that I need are, remember, we're going to try and predict the 2013 term based on the Roberts Court's decisions up until 2013. And then did I ask you, or did I just make this up for myself, to also do the same thing for 2012?
You made that up.
I made that up. All right. So I also, because the results turn out lousy, I'm thinking, well, maybe there's something weird going on in 2013. Let's look and see. If I went up through 2011, could I predict 2012 very well? And once again, I think we're going to see, I'm not so sure it's anything weird about 2013. All right, so let's look at this little chunk of code here. I'm going to construct a query on the database. This is a way of, you've got a data set, I want to get stuff out. And the thing I want to say is, you know how in R it's like data, dollars, chief equals Roberts? Okay?
Sure.
Well, this is exactly the same kind of thing. Instead of putting it in quotes, you're just going to put a pound sign in front of it. Chief is Roberts, and the term is less than 2013. Okay? And I can use the less than sign here because so far as Mathematica knows, these are numbers, and so it will do the right thing when you ask if something is less. So I'm going to construct this query. The columns that I want are all the columns in NV list 1, which is all this stuff, the petitioner, respondent, etc. And this query is going to operate on my data set that I created up here. So this is going to get me the pieces of data that I want, and then I'm going to ask it to just put it in machine learning format. So that when I do this, what I have is, okay, in the first item of data, the petitioner is 126 and the respondent is 28 and the lower court disposition was 2, etc. And there are 650, and this case came out as a 2, which I think is liberal in the Rustal eyes. And there are 650 more of these. Okay? So I do that. Now I'll do one where I say, okay, I want the chief to be Roberts, but I want the term to be 2013. So I'll do that. Here's one where I want the chief to be Roberts, but I want all the cases before 2012. And here's one where I want the chief to be Roberts and I want the cases from 2012. So I'm just creating these data sets, these sort of little mini data sets on which I'm going to run my classifications. Okay? And let's see here. Oh, here I'm doing exactly the same thing. This code is exactly the same. The only thing that's different is I'm using different columns. And here, remember, I had this idea that maybe it wasn't, that I shouldn't be predicting liberal conservative. I should be predicting whether it was affirmed or reversed. And that's all this code does. It's just picking out a slightly different set of columns. All right, so that's that. So Mathematica does not have yet, despite my request, a 0R machine learning algorithm. So I just wanted to construct one. So I kind of knew what the competition was. That is, whatever algorithm I come up with, if it's not better than 0R, which in our case is just assume the court will be conservative. Okay? That's basically the rule. I just decided to see what was it. So before 2013, there were 357 conservative votes, 285 liberal votes, and 9 of these others where Washington University and St. Louis gave up. And so if I just picked everything as conservative, I would get 54.8% right. And if I looked at it for 2012, it's roughly the same story. I would get 55.8% right. Okay? So that's my baseline. And I think that's the, when someone brags that they're getting 74% right, well, okay, but you got 58% of that for free, which is not to sneer at what they're doing, but anyway. And I also decided to look at it for disposition. And disposition's a little harder because there are all these subcategories of disposition, like there's, affirmed and remanded or reversed and vacated and all these little categories. And so actually, if we are only scoring, what we want to predict is, I think, code 4, which we could look at the Washington University site and see what is a code 4. Well, that's not what I wanted to do. How do I undo that? How do I get to this window? Okay. No. Where's my Washington University and St. Louis site? Here we go. So if I go to the documentation for it and I look at disposition of case, number 4 is reversed and remanded. That's the most common outcome of Supreme Court cases, which sort of makes sense. That's why they usually when you take cert, that's a bad sign for the
That's the-
appellee,
Yeah.
right? Okay, so same thing for 2012. All right, so I thought I would start with my good old naive Bayes. And so I'm going to take all my data before 2013, apply naive Bayes to it. I'm going to remind my system that the items in NV list are nominal variables, that the numbers don't mean anything as numbers. And I'll call my outcome NB pre-2013. Right? So there we go, nice and quick. How'd I do? Not really very well, okay? I get 57% right in predicting the 2013 cases, which isn't much better than I would have gotten for free. So, what's going on? Well, let's look at the confusion matrix. And it doesn't, I don't find here the confusion matrix to be particularly informative. It's just getting things wrong. And so, would we have done any better if we just looked at 2012? Is there something weird about 2013? And maybe we did a little better in predicting 2012, okay? And so, one of the things you can be thinking about is, we're treating the Roberts Court as a single entity, but in fact, the justices on the Roberts Court are not consistent, okay? So we have Sotomayor coming in and Kagan coming in, and so they may, and yes, they're replacing somewhat liberal justices, but not real, well, in some cases they are. But in any event, we maybe should have other variables looking at who's on the court. And maybe if we had those, it would be better. Or I could have given you the harder task of not predicting the court, but predicting it on a justice by justice basis. The predict how will Justice Kennedy come out, and maybe then aggregate, sort of have a fake Supreme Court where the justices vote to see what the outcome is. But I made it a little simpler for you, and that may be one of the reasons that we didn't do so well. All right, I also tried to see how would we do if instead of predicting the liberal conservative nature, we tried to predict the disposition of the case, meaning was it reversed and remanded or vacated or what happened. And we don't do so well. We only get 28% right. And so I think what's going on here is we have too many categories. We're trying to predict something too finely. And so one of the things that you might want to do if you were serious about this was to take a look here and say, okay, first of all, let's treat all affirmances as so let's lump 2, 6, and 7 together. Let's lump 4, 5, and 8 together. And I don't know, maybe 9, 10, 11, and 1 are sort of this other category. And maybe if we only had 3 categories, we would be more accurate. Like, it seems to me it's pretty hard on the basis of these categories to try to predict whether something will be reversed and remanded or vacated and remanded. And since no one but Aaron Brule knows what the difference between those two things are anyway, it might be a prudent idea. And for 2012, we didn't do any better. All right, I'm going to skip support vector machines for now and go to neural networks. Okay, let's see if neurals do any better. And I'll run the code. Hey,
It went worse.
what happened? Do that again.
It went worse.
It's getting worse by the minute. Why is it so sensitive?
It went up again. You said that.
What's random here? This is very interesting.
Well, we can't be sure of any of your end data at this point.
All right,
This is
so
wrong.
let's look at some let's look at a little bit here on neural networks and see if there is a seed that determines anything, because indeterminate threshold method, nominal variables, performance goal, utility function validation set. Did I set a performance goal? Not that that should really matter. No, let's try setting a performance goal. Let's go for quality. All right, now let's see how we did. All right, so this is where if one really cared, one would be sending off an email to support@wolfram.com asking why the result varies and what one can do to stabilize it. And it may be there are some random things that they're picking at the beginning, like how many nodes there should be, and that may make this fragile. I've never liked neural networks. Sorry, but that's what our matrix looks like, and there it is. If we do the same thing on 2012, that's what we get. We can do disposition, and you're going to see it doesn't do very well. Disposition again. All right, let's try good old logistic regression, see how that does. (62%). So that's doing the best. Let's also, as while we're at it, let's see if we can't get some quality introduced here. See, in my experience, it doesn't seem to matter. Same thing. All right. So far, logistic regression's doing the best. We could run it on do exactly what I've done before. All right. And it doesn't predict disposition very well. Good old nearest neighbors that we've talked about, which I always think works pretty well. And again, just to be fair, let's go for quality here. See how nice and fast it is. And 60%. Let's try it one more time. Oops. 68%, so I got lucky. So again, there's got to be some random element going on here inside these systems, and it's doing fine. All right, so we'll just run it for the rest of the stuff. And I thought for fun, I would try to stack as one of these meta methods. It's a pretty easy algorithm to implement. Remember, stacking is where you take a set of classifiers, the classifiers make predictions, those predictions become your new independent variables, and you run some machine learning algorithm on the new variables, and so you simplify your system. Like my system originally had seven inputs, which were things like, lower court disposition. The new system has 4 inputs, which are going to be, how does a naive Bayes classifier think it's going to come out? How does a neural network think it's going to come out? How does a logistic regression think it's going to come out? And how does the nearest neighbors think it's going to come out? And we'll run a bunch of classifiers on that. We'll run a naive Bayes on the stacker, and a neural net, and a logistic regression on nearest neighbors, and we'll see if any of these meta classifiers can in fact extract information that the base classifiers were unable to find. So this is a little bit of fancy code that what it's going to do is it's going to take each of the classifiers and then try and use them to say what it predicts the outcome will be on the pre-2013 cases, and then I will let's see, how does this work? All right, so let's do this. It's predicting, each of the classifiers is predicting the outcome on the pre-2000 cases. Now it's going to predict the outcome on the 2013 cases. And so if we look at what does this data look like, it says, okay, for the first case, the first classifier, the naive Bayes predicted a 2, and the second one predicted a 2, and the third one predicted a 2, and the fourth one predicted a 2. And in fact, it came out a 2. All right, and so there you go. And so now what I'm going to do is I am going to take this kind of data and see whether a naive Bayes neural network, logistic regression, or nearest neighbors can do anything with it. So we're done. And now we'll see how does it do predicting the outcome of the 2013 cases. And last time I did better. But all of these methods seem to be around 57, 58%, which is no better than my best systems. That is my best system, logistic regression. Let's run it again just to see if there's anything random about it. Logistic regression seems to be deterministic, and it's getting 62%. And so once again, the brilliantly touted method, these meta methods, which seem so clever, in fact don't accomplish anything. You're just... my sense is that if you've got really bad results from a bunch of classifiers because they're insufficiently complicated, then some of these meta methods can actually get you some gain. But where the problem is there's just noise in the data, a lot of these methods, they've done what they can with the noise. That is, they've come up with the best patterns they can, and you can keep running more sophisticated and more sophisticated, throwing more sophisticated tools at it. But the problem is, it's just noise. You don't have, maybe it's not noise. That is, it's not totally random. It's, what did Justice Kennedy have for breakfast? That's not random, but it's unknown. And so if he had bacon and eggs, he votes liberal that day. And if he had Cheerios, he votes conservative that day. But since you don't know that, it looks random. Right? The other thing I thought would be fun to do would be actually, you could see which were the most surprising cases. You could see which cases did most of the predictors get wrong. And so I did this earlier. And what was most interesting about these cases is that I had never heard of any of them. Does anyone know any of these cases? Heimshoff versus Hartford Life and Accident, Sandifer versus U.S. Steel, Cayley versus U.S., Robers versus U.S., Michigan versus Bay Mills Indian Community, and Lockman versus United States, and the United States versus Clark. I've never heard of any of them.
No.
Okay, and so I'm not sure what that proves. Maybe these are obscure cases in which, here's a theory. These are obscure cases. The judges don't feel bound to vote liberal, conservative, or maybe it doesn't have much meaning in this context. It's, two big corporations suing each other over the meaning of the proxy statement language in Section 23 of the Securities Act of 1934. And it's just a technical question. Okay? So, but nonetheless, I thought it was interesting. And then I tried to see the degree of surprisingness amongst various cases. So that's the Mathematica chunk. Anyone have questions on that? Oh, why didn't I show you support vector machines? Because this morning when I was running support vector machines, I kept crashing my machine, which it didn't do earlier, and so I think there may be an issue. When I did it the first time, I didn't do it this way with associations and data sets. I just did it sort of the older way, and it seemed to work. And then I thought I would show you associations and data sets, and once I did that, support vector machine went crazy. As I recall, it didn't do much better than the other methods. So, I think
One thing was including the lower court disposition kind of threw it off. Because, why would the Supreme Court
like they're taking the case to basically reverse it, like you said. At the
So it
beginning.
doesn't add any information.
I don't think so.
Okay.
I mean, that was my theory because like when I tested them separately, they all got negative.
Okay. So one of the things we're going to do at the end of class, I hope. Actually, this is good. This is a good segue into, I think, what's going on here. And what I assume most of you saw is Weka didn't do much better, and in some cases it did a lot worse.
It was pretty bad.
All right. So it's possible that there are implementation issues in either Mathematica or Weka which are causing these not very good results. Don't think that's what's responsible. I think what's responsible actually is that we have not applied sufficient human intelligence to the problem. And using our domain knowledge and some other machine learning techniques to try and structure this problem a little better. I think the fundamental problem is that actually, although it looks as if there are only 6 variables here, petitioner, respondent, lower court, really there are a lot more,
Yeah.
because there are, whatever it is, 50 different kinds of petitioners.
600.
Okay, but they're not all
They're
in
not
the
all-
States.
that's
Right.
true.
All right. But the point you're making is the correct one, which is that actually, I did a count. Did anyone play with actual Weka? The little birdie Weka?
You can play with them.
You can play with birdie Weka. One of the things it can do is it will say, binarize your data. By that we mean, okay, for each petitioner, each class of petitioner, it's going to say it either is a 4 or it's not a 4. Or it is a 5 or it's not a 5. Or it is an 8 or it's not an 8. And so you end up with, on this data set, 298 variables that are really present here. Okay? And so you have 298 variables, and you only have 760 or so pieces of data from the Roberts Court. And that's a pretty serious task, okay? And one of the things is, even though these computer algorithms are good, when you start giving it a lot of variables, it's kind of spinning its wheels, and it doesn't have enough to get traction, is the best way I would put it. So one of the things that people like to do, which I didn't ask you to do, is to reduce the dimensionality of the problem, to try and make it simpler. So there are human ways of making it simpler, like maybe we're smart enough to know that law type 9 and law type 8 are really the same thing. Yes, they're technically different, and issue area 14 and 13, so we do lumping, okay? So one of the ways you can do it is through lumping. Or you say, look, if there are less than 3 people in one of these categories, just lump it in together with all the other things that are fewer than 3, and just have a miscellaneous category, okay? And so you can greatly reduce the dimensionality of your data and give these algorithms a better chance to grab onto something by applying some human intelligence and recoding it. Okay? The other way to do it is to have the machine try to figure out what matters, and then to restrict your data set to only maybe the top 5 or 10 variables that matter. Okay? So how do you know what variables matter? And Weka and R-Weka have a variety of algorithms that will do this for you. I'm going to talk to you about one of them. Okay, so here are the ones that are available in Weka, and they have these obscure names: subset evaluation, gain ratio attribute, the info gain, the 1R, principal components, which is a popular one, relief F, which is what I'm going to talk to you about, symmetrical uncertain, I have no idea what that is, and wrapper subset, I have no idea what that is. So, but they're all designed to say, just look at these few things. Okay? So let's talk a little bit about relief F, which I have found to be a good one. All right. All right, so I'm going to create a situation here where I have 100 instances of 10 variables, right? So let's just do that. So I now have RR storing 100 rows of 10 variables. These are just your independent variables. And I have a little function here, which is you do not have to know what this is. It's a Boolean function. It just takes some values and it ands them and it ors them and it ands them and ors them again, and out pops a number 1 or 0. But it only cares about 3 values. And so what I'm going to do, and again the details don't need to bother you, is I'm going to run this function on all this data and call the output RR3. And I don't remember why I called it RR3. Okay? But what this means is that in reality, the machine never looked at the 4th value, 5th value, 6th value, 8th, 7th, 8th, 9th, 10th values. The only thing it ever looked at in classifying was at the first 3 values. The rest is garbage, it's noise. Okay? But when you're presented with data, you don't know that. You don't know that the 4th and 10th through 10th variables are irrelevant and that only the first 3 matter. So the question is, how could you figure out that only the first 3 variables matter? And yes, you can try things like, doing a regression, a logistic regression, and seeing what seems to have an influence. But this function isn't amenable to that because it's not a linear function. It's the Boolean function here is not linear. That's why I picked the Boolean function. And so a linear regression wouldn't capture it. Okay? So you need, in general, a more sophisticated attack on this problem. All right, so ready for the sophisticated attack? Here's the sophisticated attack. What we're going to do is we're going to take RR3, right? And here's just look at RR3. Oh, well, that's not very helpful. All right, there it is. Here's the data, here's the class. And we're going to group it according to the class value, so that all the things that are all the points that are 0 are together, and all the points that are 1 are together. And here's what we have. So we'll run that, and what you can see is this is saying, look, zeros consisted of all these points. This one, and this, and this one, and this one, and the ones, wherever they are, consisted of all these points. Okay? So you've now got the data separated into the 0s and 1s. Okay. Now what do you do? What you now do is you find for each value that was a 0, you rank the points that were also 0s according to how close they are to the point. So for example, here, if we were to do it, this is not going to be a very good problem. Okay. Zach, you're going to need to change your gender for the moment, all right?
Okay.
So, supposing we were to separate this classroom into boys and girls, and we were then to go through and say, who are the 3 nearest boys to Dan? We'd pick you, and you, and you, and then we'd pick you as a girl, and we'd say, who are the 3 nearest girls to you? And it would be you and you. And so we would get a listing of all of for each person, we'd know how close everyone was in your class, right? And we know the distances. What we could then do is to look at various attributes of the people that seemed to be near you, who seemed to be of your class. And so we might ask, are they wearing glasses? Okay? And actually that might work fairly well in this class. We could say, do they use a Mac? And that would not be a very good separator. Are they wearing a vest? And actually that would work, or an over something other than a shirt. And that actually might work pretty well as a distinguisher. Okay? And so that's the concept behind this code. So we're going to take, this is for the zeros, this is for the ones, and then what we're going to do is we're going to find for each attribute, glasses, more than a shirt, Mac versus PC, who knows what else. We're going to see what is the mean value of the neighbors, and what's the difference between the mean value of that attribute for your neighbors who are zeros and the mean value of that attribute for neighbors who are ones. And the difference between those means is some measure of whether that attribute's doing a good job distinguishing the two. And what we'll then do is we'll take the average for every single person. So that, yeah, maybe it's a good thing for Zach, but it doesn't work very well for others. Okay? So here's what we do. And here's what we know. It worked so well this morning. Mean transport and does not exist. How could it do such a thing to me? N goes to name 7. Let's try this. Oh, hold on. Let's start with the clean kernel. That always is a good idea when things go badly. There, it worked. All right, and if I look at the scores here, the scores for the first 3 attributes are like negative 0.25, negative 0.27, and negative 0.18, which are somewhat large, whereas the scores for the rest of the attributes tend to be a lot smaller. Now, yes, this one's 0.068, but do you see how these are showing up a lot more? So this magical technique works pretty well for a lot of situations. And it's not that difficult conceptually, I think. And so what we could then do to figure out what this function really is just pick maybe the first 3 items in our data set and run machine learning on that. Okay? So that's the concept behind Relief F. And my belief, and actually my experience, is that when you do that, in fact, I did that here. I used Weka this morning. Where's Weka? Come on. Little birdie. Here we go. To rank the attributes, and I know you can't see this, and I don't know how to make Weka be bigger, but apparently the biggest thing is whether the lower court disposition was liberal. That's the biggest predictor of what the Supreme Court is going to do. Whether the petitioner was a 28, that's also a good predictor. Let's see what a petitioner being a 28 is. A petitioner being a 28 is the petitioner a state? Okay? Is the lower court disposition direction liberal? That's important. Is the issue area number 1? All right, let's see. What is issue area? Issue area. Criminal procedure. Okay. Is the lower court disposition direction conservative? Is the respondent a 126? Let's see what a respondent 126 means. where are we? Respondent. 126 is a person convicted of a crime. Okay? So, for what it's worth, I mean, I'm not sure if it's a good sign or bad sign, but this sort of corresponds to one's intuition about what might be a good predictor as to whether the Supreme Court's liberal or conservative. Like, they're not too really big on people who have been convicted of a crime a lot of the time. And so we might, if we were doing this more seriously, try to restrict ourselves to only these, maybe the top 20 variables, and see if we could do a better job. Little plug here. Next semester there's a course called Computational Law or something like that, and it's a project-based course where you could apply what you've learned here, and a very nice project would be to do a serious job on U.S. Supreme Court predictions and to piggyback on what you've done here. All right. Off to our land. Off to our land. R, okay. And window. Ta-da. Okay, so I sucked in the data, which was an R format. I loaded RWeka, and I loaded dplyr. I renamed my data to be called data rather than this long thing, and then I just removed this so it wasn't cluttering up my environment. All right, I need to pick out some columns. Here are the columns I wanted, and I now say, look, one day I'll learn this. Take the data for which the chief is Roberts and only take the columns in question. Turn them all into factors. They're all factors. And then treat this as a data frame. But we don't need column 4 anymore, the chief anymore, because I've made them all Robert, so the chief is no longer relevant. And then I'm going to use this table df thing, which ended up not being very important, just so they print out nicely. If you look in the dplyr package, you'll see a discussion of table df. All right, so now this is all dplyr stuff. I'm going to say, okay, let's split up our data into various subsets that we're going to use. Through 2011, start with your S-Court data set and filter it so that the numeric value of the term is less than 2012. And I put an L here. If you want to force something to be an integer in R, you just add an L to it. That way it will think of it not as 2012.0000, but it'll think of it as the integer 2012. I don't think it made any difference here, but there you go. And similarly, if I want the stuff through 2012, I want everything except for 2013. This is creating only 2012. This is creating only 2013. So I still have factors. My data is still factors, but I filtered it according to the numeric values. And I just wanted to see, well, what does this look like? So here's a summary of what the data looked like through 2011. And one of the things that's important is I sort of wanted to see, what does my class look like? How many things am I having to predict? And it's saying 319 ones, 245 twos, and 8 threes. So I only have 3 classes to predict, of which really it's mostly the first 2 classes. All right, I'm going to create a formula object. This is what I'm going to be predicting for all of them. Decision direction, and here are the things I'm going to be using: petitioner or respondent, etc. Here what I'm doing is I decided I would take every darn classifier I could find in Weka that I could get to work. There are some that are listed that for some reason, I think it has to do with the libraries, that it couldn't find them. But here's everything I could get to work that at least I thought was interesting, including ones that I have no idea what they are, like a Hufting tree. I don't know what that is. But what the heck? Let's see what happens. Bayes net, by the way, is sort of a more sophisticated, it's not naive Bayes. Remember, naive Bayes assumes that none of the variables are related to each other, whereas Bayes net sort of attempts to ferret out the relationship amongst the variables. And what's interesting is usually you don't get that much of a gain by doing it, which is why people like naive Bayes. That may be stupid, but it tends to work. And I have one support vector machine, the SML reg. And what I'm going to do here is I'm going to create interfaces. I'm going to make Weka classifiers, that's the rWeka function, out of all of these methods. And I'm also going to create a function that takes the that was supposed to have been fixed, takes the output and pops out the percent correct and the kappa statistic, which are pretty good measures of how you're doing. All right, so let's run this on the data through 2012 and see how we do. Okay? This is resubstitution error, basically. And so what we see is, here's what we're trying to beat, 55.54%. 1R, which says find the one variable that splits it best and use that, gets us a little bit of gain. Naive Bayes gets us up to 58.7. Bayes net does worse. And here are the things that I still don't quite understand what's going on. Decision table is worse than 0R. Logistic model tree is worse than 0R. JRIP is worse than 0R. And the best one here are these nearest neighbor ones, which are popping in at 60 and 61%. So this was very troubling, and I don't have a good explanation for why it's so bad. And it's particularly troubling because when I try to let's look at, hang on one other second. If instead I do it as a cross-validation thing, I say calculate how accurate the classifiers are, but do cross-validation. I would have thought that if anything, my accuracy would go down because I'm asking it to cross-validate. But instead what happens is it goes up. And again, this is mysterious, and things that weren't doing very well before, like logistic model trees, are suddenly doing pretty decently. I've been playing with this for a while. I do not have a good explanation of why these numbers are so low. My opinion is that these are probably the correct numbers. That is, when I'm doing cross-validation, these are giving me accurate ideas of how well I'm going to do. And it's basically saying when you confront new data, you should expect to be getting 65, 66% right for most of these methods. Okay? The best one looks to be, is it the Hufting tree? The Hufting tree. All right. So whatever it is, it did okay. Well, let's see though. So far I've only looked at the data through 2012. So the question is that data representative of what happens in 2013? If it is representative of what happens in 2013, I should get accuracy figures that are kind of close to these. If something changed in 2013, then I may get lower figures. I shouldn't get higher. And so we're going to see, did the court change course in 2013? And I think it might have. Okay? These numbers are, I don't have a statistical significance test, I have an intuition test. These are substantially lower values than the cross-validation numbers. And so unless this is some elaborate Weka bug that I have not figured out, this is suggesting that the court changed direction in 2013. And if you actually look at the liberal-conservative split in 2013, does someone have this running live? Someone tell me how the court voted liberal versus conservative, but only in 2013. So by the way, I was sufficiently troubled by this that I decided, you know what, let me try a simpler method than cross-validation. Let me use the holdout method, where you say, okay, let's take 2/3 of the data, let's train on the 2/3 of the data, then let's test on the remaining 1/3 of the data, see how we do. And so that's what I'm doing here. And again, these methods are falling down. And so this result is not much better than what I'm getting in 2013. And so to be honest, at the moment, if my only tool were Weka, I would say I am not sure what is going on here. I'm not confident that somewhere between Weka and our Weka, I fully understand what this system is doing, because it's giving me results that I don't understand. And partly because I didn't understand the results, I decided, well, maybe 2013 is just weird. Let's run it for 2012. And when I run it for 2012, I get very similar results, where things like decision table and JRIP do dreadfully. These nearest neighbor methods do well, but when I cross-validate, let's go back. When I cross-validate, suddenly these other methods perk up, and I would be just, faking it if I told you I understood why this was happening. And then I decided, well, maybe it's because the people at Washington University in St. Louis, maybe their coders changed. Okay? Maybe the new coders have different ideas of what's liberal and conservative, and so it's just not doing a good job. So I decided, all right, well, maybe they don't understand what conservative and liberal are, but surely they understand what an affirmance versus a reversal is. So let's run it on that instead. And the problem here is that if we're really going to do this seriously, you need to spend more effort, because I've got the same problem I did before, where we've got too many classes that we're trying to predict. We're trying to predict the difference between a vacate and remand versus a reverse and remand. And so we're getting lousy numbers across the board. Same thing in 2012. So that's what my little exploration found. And so to me, the big picture is, first of all, even with some fairly sophisticated methods that we've seen are able to figure out what mushrooms are poisonous and not with 100% accuracy, okay? They are stumbling pretty badly on Supreme Court prediction without a lot of human intelligence being added. That is, we're doing a sloppy job on this, which is what I asked you to do and what I've demonstrated here, isn't good enough for this hard a data set. And that you're going to need to mix in some thinking about reducing the dimensionality of the data, using some domain knowledge about what might be really the same class, like lumping vacate and remand with reverse and remand together. And with that, you can do better. The best I've seen, I think, is about 74% on affirm reverse, and I am looking forward to speaking to the people who did that about sort of the details of how they got that high a number. I think when I've done it with CARE, I've gotten like 68, 69%. What they did is they cheated. That is, they added in things that they sort of knew about the case that weren't in the WUSTL database, which isn't cheating, that's smart. Anyway. And if you're interested in this, I mentioned you can go to Fantasy SCOTUS, look up Fantasy SCOTUS, and there are contests where you can try to predict it.
You can just go to Vegas.
Or you can
They take bets there.
Is that right? On the other thing I would say is that if you apply this in your lives outside of here, it likely is not going to be in the predicting the Supreme Court thing. It's going to be in predicting something else. But what I hope you've seen through the past, whatever it is, 5 or 6 classes, is sort of the strengths and limitations of this methodology, that you can do better in many instances than just sort of the human eye looking at data, and the machine is pretty smart about picking up patterns that you might not perceive. But you need to be very careful doing this and really think through, what are you asking the machine to do? How likely is it that you can replicate these results? and how can you kind of work together with the machine to do better, as well as interpreting the results. One of the things that's a little troubling about a lot of these algorithms is that their results are uninterpretable. It's just this black box, like a neural net is just a support vector machine. You cannot go to the average layperson and explain to them what is going on in those things. It doesn't correspond with our human intuition. They think very differently than people do. Others, like are here, I ran JRIP just to see. I ran it within Weka itself just to see when I ran it inside Weka what it was finding, because it was doing so poorly. And one of the nice things is that it is capable of telling you what it's doing. So basically the JRIP algorithm, which got 65% right on cross-validation when run through Weka, it came up with the following rule. If the issue area is 11, then assume that it's going to be one of these weird cases. What is issue area 11? I wonder if it's like original jurisdiction. You know, the Supreme Court has interstate relations, so that may be state versus state, where what does it mean when they decide that the river goes to Oklahoma rather than Texas? It doesn't really fit on a liberal conservative spectrum. All right, so what else let's see, what else could we do to predict? Wait, I need our Weka, the birdie. There's the birdie. If the lower court disposition was conservative, then you should predict that the Supreme Court's decision will be liberal. Okay? And otherwise, assume that the decision is liberal. That's its rule. That's all it is. Okay? Incredibly simple rule. And that rule gets you 65% right. So let's actually, as long as I've got this data up here, let's try another algorithm. And we'll run it within Weka. Let's see how a decision stump. Why can't I run J40? Let's run a decision stump. Okay. How's it doing? Is it going to tell me how it did? It is not going to tell me how it did. Well, here's its rule. If the... I don't understand this interpreting... It's looking on... The thing it's looking at is the disposition of the lower court. So it's liberal versus conservative. And my guess is it's telling you, if the lower court disposition was liberal, assume it's going to be conservative. If the lower court decision was conservative, assume the outcome's going to be liberal. Because they usually reverse.
Yeah, that's right.
But why won't it give me... Why is it blanking out J48? I don't know at the moment. Let's see. That's not interpretable. Linear regression's kind of boring. I can't give you an answer as to right now why Weka is not cooperating. All right. In any event, there are also clustering algorithms, all sorts of fun things within this little package, where if you don't want to use R programmatically, you can go directly into this. I will tell you that if you're doing anything serious, I don't think it's too hard to be clicking 17 different buttons and remembering the sequence that you clicked them in. That is, you might get a result, but it's not replicable, and that's an advantage of using a program to attack this. So, anyone have any questions on anything? Yes?
Do you mind putting these up?
Right. Let's do that right now. Okay, since, as you know, I sometimes am forgetful about this. All right. Access UH. Those of you who've been following the saga of my password know that I've changed it. All right. so we're on day 15. Build content module page. Day 15. Here is the Mathematica Supreme Court notebook. Here is the RMD file on predicting the Supreme Court. You will need to edit it to insert your own file path to the data, because I put it on my, I think it's from my hard drive, same thing. Here is the Relief F notebook. Anything else that you need from today's class? All right, let's do this. Attach. Browse my computer. Analytic methods. Course materials. The RMD file. Browse my computer. Supreme Court predictions RMD. Relief F. Which, by the way, if you're thinking, if you're one of these people and all you care about is what's on the midterm, you're not going to need to know Relief F to do the midterm. That is for your general edification, okay, things to know. Where is explaining, and by the way, if you open Relief F, you're going to see that notebook is a mess, and so just look at the first couple of pieces of it. Submit. Okay.
So you asked at the beginning of the class, like, the benchmarking,
Oh yeah, what are you?
point 11.
Okay,
That's
so
pretty low compared to what he had.
Yeah.
I will keep that in mind when I'm making the exam. That it was in mind that it should be simple. That the data should not be massive or complicated. It should be manageable, and you have reinforced that because it would not be a good result for you to be, waiting 10 minutes for it to churn through something that other people
Right.
are getting in 2 minutes. Yeah.
Have we figured out where the exam will take
Yes, it is in BLB
It's
1,
in papers
which is
class.
the old copy center. And you will need internet access. And I will print out a copy of the exam so you can have that in front of you. Office hours, I'll be here between about 10 and 2 tomorrow, should be open. And, Wednesday, if you're panicked before class, come see me before class and I'll try to help you out. It's going to cover, what it's going to cover. It's going to cover statistics and machine learning, and I've told you the scenario is sort of going to be a deposition where you get an hour and a half lunch break in which to figure things out. And then,
So technically, then we should have the questions beforehand, right?
yes, so it'll be an hour lunch break. The good news is, I think this is the hardest thing we do in the class. The machine learning stuff, I think it's the most complicated. Finance, piece of cake. Piece of cake. It's going to seem so easy, and it'll draw a little bit on your knowledge of statistics, so don't forget, after Wednesday, don't forget your statistics. Decision theory, not so bad.
if we do a lot of stuff on networking can get complicated, but we're only like spending a day or two on it at most. So, the good news I think is that the hardest part is done. All right, have fun. Stop recording.